You would even think that like in a high reliability industry, like, defense, aerospace, even medical, automotive, those kinds of industries, that there would be a willingness by somebody, right, to invest in building these solutions. I'm just a little bit surprised that like the lack of investment is really that bad.
Yeah, we've both been in the industry long enough to say like, yeah, we're not surprised. But then when you look at the financial ramifications of what it means to the company and their product, right? Everyone talks about how they can build the best boards, the best density. If you can't measure and assure that you're doing that or build that kind of a product repeatedly, how do you make those claims as a business owner and then, feel great going home at night?
Hello, everyone, and welcome to the Altium OnTrack Podcast. I'm your host, Zach Peterson. Today, we are joined again by Geoffrey Leeds, founder of Scan Labs. This is Geoffrey's third time on the show. Very happy to have him back after a great time at Apex, and we're going to be talking about his new company. Geoffrey, thank you so much for coming back on the podcast.
Yeah, Zach, thank you so much for inviting me and having me back on. Pleasure to be here.
Yeah, absolutely. So for those who don't know who the heck you are, we had you on, I think a few years ago when you were still working at Inselectro. And then I know you left to go do some consulting work with Leeds Engineering. And then now you have stepped into a new role, founding a new company called Scan Labs. And so that's kind of the background for everyone that's watching the show right now. So before we get into all of that, I want to encourage everyone to check out the links in the video description. If you're watching on YouTube, go watch those old episodes because they are still very good and very relevant. And now we can get in to catching up with you. How's everything going? It seems that's a lot to go into, right? But at the beginning of a podcast.
Yeah, I appreciate the wind up there. No, it's been a fun, wild couple years. Like you talked about, we first met when I was at Inselectra. I just finished doing something in Washington, D.C. The CHIPS Act was still new and novel, and there was excitement around how we're going to, onshore IC substrates as well as other downstream processing. And then from there, came back on a couple of years ago when I started my own company, Leeds Engineering and Data Science. And I started it with my business partner, Dr. William Leeds. And the idea was that we just go do consulting. And I was stepping into this world of data science and AI. And I'd done a lot of internal model development in 2019 to 2021 and done some proof of concept stuff at Inselectro. I totally missed the whole LLM and agentic phase that came out. Like, full disclosure, I did not think that was the world that AI was going to go back then. And our initial thing was to just go help out people, companies trying to figure out to implement data science, advanced manufacturing, consulting, etc. And what it took us down was this pathway of, what are other big problems out there that we could potentially solve? And one of them, when we were talking to electronics manufacturers, was this third-party lab problem. So most PCBs that are made for class 2 or class 3 or any high reliability world, we have to make the circuit board, but then what you're really doing is you're really buying the coupon in the report, because at the end of the day, that's what gets destructively analyzed to certify whether or not the boards were built to your specifications. And in my time in the industry, everyone talked about third-party labs taking forever. They cost a lot of money. There's a huge issue with them, blah, blah, blah. When I stepped out on my own and we had our consulting company for a while, we heard the same thing from OEMs. And to me, that was the most interesting thing, was hearing from some pretty big DoD primes about how they're 6 months behind on internal sectioning and qualification, as well as external sectioning and qualification from their supply partners. So like any good engineer, you think you can solve any problem. And it's like, okay, let's go figure out what are the nuances here. What's the true problem? And what it really led us down was this world of identifying essentially what I've been calling, the metrology gap. That as semiconductor or other manufacturing nodes beyond PCBs or deeper into the IC or interconnect technical stack go, metrology has kept up with that scale density because it's very costly. But when you're selling a chip from a wafer that's $20,000 a pop, it's pretty easy to justify these multi-million-dollar tools in very specialized applications. But we have not seen that same trend keep up with the PCB world. So as PCBs have increased in density, we've been relying on traditional or heuristics-based analysis of micrographs or microsections to identify whether or not a board was built properly. So even though densities keep scaling down, Microvias keep getting smaller and smaller, we had to manually cross-section and grind to validate whether or not these structures were built properly. Whereas in higher technical stacks, right, they've automated this as much as humanly possible. So the idea is how could we potentially go and look at some of these learnings from the semiconductor world or heterogeneous integrated packaging and really bring that tech to PCB manufacturers, but still utilize the same form factor and function of the coupon. And we believe we've cracked the code on that. So Scan Labs is a pretty automated, I can't say fully automated yet, we still have some steps that aren't automated, third-party inspection and test laboratory that specializes in microsectioning for electronics verification. So we have a completely automated, serialized grinding piece of equipment. So we can actually take coupons. I was like looking around, I had one right next to me. And we can, once we have it in the puck, it's completely hands off and it does all the grinding, imaging, etching, and then imaging again per IPC TM 662.6.1.1 without any human interaction at all. And the benefit of that is that we can then start essentially aggregating pictures and data at scale. And because it's automated, we have high reliability and trust in these data sets that are being generated. So we don't have to say, oh, this operator generates good reports, or this person is the only one who can rely to do it. The automation is incredibly consistent. That gives us a really high value data set that we can then turn around and give that directly to manufacturers at speed and at scale. And then we can start applying algorithms, all kinds of other crazy stuff to the data assets. We build complete digital twins for every single coupon that we get. Our GD&T process gets us down to 700 nanometers accuracy on the outer layers for both top and bottom. And then we can correlate them spatially to one another. So that's the whole correlated metrology bit. I'm pontificating on all these different things that we can do. So I hope I'm not just like dumping on you here. But what I'm getting at is that we've basically found this world where, you know, microelectronics manufacturers don't have access to metrology data that will allow them to improve their process because there's been no one putting effort into trying to figure out and understand why this exists. So that's really what we looked at, and we figured out how we could bring in just high amounts of automation, both physical and software, to get to the point where we can pump out a coupon completely analyzed per 6012, 6013, or 6018. Once the automation is going, about every 6 minutes, we get a completely analyzed coupon. So we can pump out at scale huge amounts of data analysis for our customers. And the hope is that we can help the, you know, North American as well as other high reliability marketplaces that rely on cross sections to be able to continue using them, but then step into this world of semiconductor information and know-how and apply it to a bigger form factor.
Okay, so there's a lot there.
Yeah, sorry.
No, it's fine. Let's take it one by one. So, okay, so microsections, right? So, I would think that quite a few folks in the audience, maybe they haven't worked in manufacturing. If they know what a microsection is, they probably assume to some extent that, you know, every fabricator that they work with is going to have reasonable, you know, capability to take these microsections, and that there's, you know, equipment available that more or less automates the process. And you're basically telling us that that's actually not the case. If you go and talk to the customers of those fabrication vendors who have this big backlog, especially in this high reliability world that really needs to rely on accurate, repeatable microsection data.
Correct. In fact, our first customer that's been supporting us was actually a PCB manufacturer who couldn't hire and retain talented individuals who are really good at doing microsectioning. It's the sectioning needs inside the factory greatly outpace their ability to hire talent to be able to perform them internally, and then also do the sectioning reports at the very end of the process. So they're stuck with having to do in-process cross-sectioning checks and end-process cross-sectioning checks, and it's becoming too much to bear, especially as we start getting into these really high-density world. So that, yeah, I think you summarized that really well. As it was, you know, we found it on both the manufacturer and the OEM side that it's highly manual, it's very operator dependent. There's a lot of stochastic variation in that process, and sometimes, I mean, you'll even see it. Some operators do things a little differently. So there's this like heuristics based approach to who can get the better data or the better information from a cross section, but it's really kind of the Wild West, which was surprising to us.
Yeah, I also think, I mean, my only exposure to this has been with like electron microscopy, where
Mhm.
sometimes you need to, etch into something maybe with a focused ion beam, and then you're taking an image of a cross section. Maybe you're doing it at an angle, but regardless, some of the things that you mentioned just now are really prevalent there, especially operator experience and experience with particular machines. I think when you look at PCBs, they're just larger scales. You wouldn't have assumed that this would really be an issue with PCBs. And I guess I'm a little surprised to learn how heavily dependent it is on operator experience, and that there hasn't been really any kind of level of automation to help deal with that.
Yeah, and I want to be clear. There are some companies that do have semi-automated grinding and polishing pieces of equipment. So Allied, I've got one of their boxes right there. Allied High Tech, they sell something that is semi-automated. So once you've made the puck, you can put it into their auto grinder and you can program in different recipes for the polishing and for how much pressure it applies. They have this whole system that allows you to have like stops, pre-configured stops. So you can say, okay, I need to go down 2 or 3 thousandths of an inch, right? And it's pretty good, don't get me wrong, but there's still some inherent problems with that, right? Is that one, there's still stochastic variation in terms of like, okay, are you cleaning the platen? Are you replacing the sandpaper on the right scheduling, on the right time? Is your water clean? So there's all these other variables that will actually affect the polisher itself and then the resulting micrograph and data you get out of it. And really trying to just take that part of the cell and say, let's automate this, because as you again scale down to smaller and smaller features, if you've got, let's say, an AB coupon, 4 microvias, and you're trying to hit a 6 mil of a 6 mil pad, let's go with that. So roughly 150 microns. So plus or minus 10% per IPC. So you're looking at a 30 micron window where you have to put the micrograph to ensure that your measurements are valid. But you've got 4 of these on one side and maybe also on the bottom. Now you have to put a plane between all of those to just have some kind of certainty that the measurements you are performing are consistent. Or let's say you only hit 1 or 2 microvias and you need a third one to take a look at. You don't get enough information to start doing really deep statistical analysis, which is what the semiconductor industry has been doing with metrology for decades, which is amazing to see them solve these issues. But we really lacked the ability to take a truly data-driven approach to how we perform micrographs. So like our piece of equipment, we actually know ahead of time based on all of the registration and previous information to then know that is there a theoretical perfect cross-sectional plane that'll hit everything? If not, we actually can serially step through it. So we'll step through to the very first one, take a micrograph, and then grind down a little bit more to the next plane, take a micrograph. So we can hit all of the center of all the microvias essentially that we want to, or any other drilled feature, and then really develop some pretty substantial descriptive statistics. And then from there, some other really fun spatial analytics. But it's not something that's possible today with the current equipment set that is being utilized by the industrial base.
So that gets into my next point. And I was going to ask, how exactly is this done with legacy tools and relying on operator experience versus what you're doing? And I think you've hit part of it, which is the existing equipment can't really do it so well. So does that mean you're making totally new equipment, or you're just improving on the existing equipment?
Yeah, it's pretty heavily customized internal automation equipment. We've purchased existing equipment and gone through the modification process for that as well, because there are some throughput benefits by using existing hardware.
Sure.
They want to make them generalized. Like Allied sells tons of metallographic equipment, but none that are specialized to the degree that we have for PCB microsectioning and metallography. And so that was really the niche we took a look at. When you look at what's going on in biological or pharmaceutical labs, there's tons of automation that's available to you because they've all standardized around sample sizes, And I looked at our industry and we have standard specimens, right? The IPC coupon's pretty standard, it's utilized, but there's no automation that is centric to these coupons. So we took a look at it and said, what if we just made all of our own automation and customized our tools and our process flows around this to really improve our throughput? And that allowed us to also really improve the quality of the data. And it's been a wild ride, but the overall market does not have specific tooling or just any handling equipment that is so specific to what we're doing that we can be using at scale. So we've had to customize pretty much everything: our microscopes, the inserts to the microscopes, custom software to extract the data. We do all of our correlative metrology with a couple bespoke internal models and configurations. That would be Dr. William Leeds' math background coming in there. Pretty fun trig. And some other stuff. And really just figuring out how to make everything work has been a little bit of A, a little bit of B, some completely designed internal tools, some off the shelf stuff. But it seems like a Frankenstein at first, but it's now all finally coming together. But yeah, it's a lot of internal heavy customization, I would say.
So it sounds like some of the big challenges that you're addressing by doing all of this, right? I mean, you mentioned operator experience, right? So being able to remove the dependence on that, I guess, translates into consistency, right? Mm-hmm. And then I think you mentioned you're producing a microsection every, I think you said 6 minutes or so, something like that.
Yep.
So this also sounds like throughput. So you're able to really do both by taking some automation steps and then applying those directly to the existing equipment in some customization as in other areas as well, and then custom software. And by doing that, you're able to really address both areas.
Yeah, it's for hyper niche applications like this, especially when you look at like what semiconductors, then you have to. There's a lot of domain knowledge and information you need to know about the specimens you're looking at, which is what I was able to bring to the party. And then looking at all of the papers and publishing that's just gone on in the semiconductor world and metrology in general, and how they've solved some issues pushing past 20 nanometers without tools that have accuracy and budget constraints that they could meet. So they had to come up with all kinds of different techniques for it. So when you look at what metrology equipment is available to us, and it's like, okay, optical microscopy is the number one thing that everyone uses. It's how we produce micrographs. We all know how to read them. We believe there's people aren't extracting all the information they can from that. What could we do to really tackle that? And it's you really have to know both sides of the equation to be able to understand the assumptions that are being made in some of these decisions, and then how do they apply to the end product and result, and to the data assets themselves, to understand the nuances of what this measurement truly means. Yeah, it's hopefully that made sense, but that was like this whole research pathway that I had to go down to really stop and say, okay, why don't we have any metrology equipment that can solve these issues we're facing? Like, why are we stuck here? Why does the industry think PCBs can't advance? And it's because we haven't really been looking at how we perform measurements and deciding whether or not something is good or bad. But we still have the ability to extract all that data and more from a standard IPC coupon. You just kind of had to know what to go back and iterate over.
There's two things I want to bring up here. One of them, though, is something you just mentioned, is actually something you mentioned on the first podcast, which was related to microvias in PCBs. And I think we were talking originally about stacked, blinded, buried microvias. And back then you had mentioned, yeah, we figured this out by looking at what the semiconductor industry did. They had solved it 2 decades ago in packaging. Yep. And I feel like we keep coming back and having to do that, because you just mentioned it again here. And then I took what you said to heart in some of the seminars that I've given with signal integrity, getting up to the 56 gigahertz and higher bandwidths, because they figured it out in packaging. We have to figure it out in PCBs. So it seems like we just keep piggybacking off of the semiconductor guys in terms of, finding solutions to some of these challenging problems.
No, I'm so happy to hear that you took that to heart, because that was kind of my whole take too. I was like, someone's got to have figured this out. And then when you look at, an IC substrate, and then you look at how semiconductors are made, it's a transmission line. It's the same thing. It just has different materials and a different process to make it. And so if you put your material science hat on, it's like, okay, my properties of whatever, material I'm looking at are changed by the manufacturing process, which then change its performance. And I was like, okay, so looking at what was going on in the IC semiconductor industry, it was the same thing. What were they limited by back then? Well, it turns out that Angimoto didn't exist, for a long part of it. So they were facing the same problems we were with FR4 substrates, with non-homogeneous reinforced materials, aka glass weave and resin. It's like, what were they doing? And there are some fantastic papers that were published. And I'm happy you looked at the transmission line stuff, because for me, I can do Newtonian physics and I'm there, but I know like you and I have talked about getting into some of the really hardcore physics and more quantum metrology, right, is probably where that gets into when you start trying to solve some of the I always forget the name of that physicist and his equations for electrical Maxwell's equations. Thank you. But yeah, we follow them. We follow semiconductor. It's the same structures, different materials and different process. So when you stop and you take a look at what are we doing, what materials are we constrained to, we have different materials than what they had, but physics doesn't change, right? Like it's not gonna be drastically different, but it gives us a blueprint, or at least a path to start following. And it's, to me, it's incredibly eye-opening to do it. So I appreciate that you went and did the same thing, and it's fun to hear that you found it on the transmission line stuff. I'd love to pick your brain about that sometime.
It was actually more on vias and via transitions into packages, but there's another aspect of a certain type of transmission line that it applies to as well. But I've made the joke a few times. We often say that semiconductor people don't know anything about PCB design, and that's true, except for when it relates to a package. Yeah. When it relates to packaging, they're way, way better at that stuff than we are. So we should probably follow what they say.
It's very interesting, because the other angle you could put your hat on and take a look at it is that they're so hyper constrained, though, to very few material sets. Like GaN presented a lot of issues to them, right? The residual stress from GaN silicon and CTE mismatch was a huge issue in power electronics that I wasn't exposed to until I started doing my own research on like Microvia CTE expansion, and then seeing what was going on in the GaN world. But when you look at IC substrates in the packaging world specifically, they're constrained. Okay, silicon being, the big one, right? And then the IC substrate was Angimoto. So those were their two big commercially available materials that everyone understood pretty well. And from a big data perspective, that's actually not that great, because if you look at the 5 V's of data, so if you want to start thinking about how to look at what data assets you have and how can you use them and extract them for the max amount of information, it's like volume, variety, veracity, velocity, and there's another one in there. But variety is the one I want to focus on, because the variety of information or materials that they use are limited compared to what we do in PCBs. Like you go into any board shop in North America, Europe, anywhere in the Mediterranean, you're going to walk into their materials room, and there is 50 to 60 different materials at any given point. And they have developed their processes to be able to use all those different materials and then quantify how their process controls need to behave in order to make these microstructures. So they're actually sitting on quite a bit of valuable information in terms of how to change manufacturing processes to affect the ultimate structure's capabilities. And then it was like, okay, that's great, but then how do you validate some of that information? And that was part of the angles that we took a look at when we were creating this company, was how do you validate, right, this information? How do you validate that those structures are good? And part of the problem that we found is X-rays are great. They do a lot of great, non-destructive analysis, but there's an inherent limit to how much resolution they can get. So when you're looking at registration, you're looking at the different targets in a board, that only gets you so far. And that uncertainty in the X-ray and millimeter level precision doesn't hold anything when you start looking at you can't get the same fidelity of information out of a micrograph. Like the micrograph is going to give you sub micron into nanometer level precision, depending on what your optics look like, right, and your sensor. But that information can tell you all kinds of stuff about what's going on in terms of registration at that scale. So when you look at what semiconductor has done, they love SEM and they love, like you were pointing out, FIB, because they can incorporate that straight into a tool. They're already working in vacuum-based environments. They don't have to take something out and go prep a sample. They can do it literally in line. And one, I love it. I love the automation from that. Like that just makes the nerd in me freak out whenever I see how these tools are incorporated in. But then you look at a board and you're like, we don't have, it's like, okay, where can we start getting some of that information? It's like, well, the micrograph actually has all the information we need given the scale in which we're operating. So for us, it was like, all right, go back, look at all the semiconductor stuff. When did they make their transitions over to SEM EDAX, right? Why couldn't they use micrographs? There's issues when you go below like 1000x resolution with air, you have to switch over to oil. So it's like, okay, so here come the design constraints. But it was quite the fun to go look at why semiconductors stopped or why IC substrate stopped performing and using micrographs the way we do, and then us coming along and saying what technology exists that allow us to extract even more information for manufacturers and for designers, because we can take all that information straight out of the coupon and give that back to the designer. So if you wanted to rerun your transmission line models, if you wanted to rerun thermal analysis, we can give you back a complete SolidWorks object part file. So you could throw it into a finite element analyzer and then see whether or not it works as built versus as designed. And then you can start quantifying what the error is for every panel. And because we break it down per coupon, we can start doing spatial analytics to really get to the point where you can predict what boards on a panel are going to be the best performing boards or the closest to the blueprint. Because guess what? It's what semiconductor does. So it was really trying to just figure out like, okay, how do we pick apart this animal here?
So we'll get into that in just a second. But the other point I wanted to mention or maybe ask you about is, what you're talking about here with bringing some more automation and innovative solutions to what is clearly a problem across multiple fabrication vendors and is obviously a problem for customers. I think it reflects the lack of investment in our industry. And you would even think that like in a high reliability industry, like, defense, aerospace, even medical, automotive, those kinds of industries, that there would be a willingness by somebody, right, to invest in building these solutions. And, it clearly hasn't happened until, now you're in the game. So maybe some others will follow, but I'm just a little bit surprised that like the lack of investment is really that bad. Maybe I shouldn't be surprised.
We've both been in the industry long enough to say like, yeah, we're not surprised. But then when you look at the financial ramifications of what it means to the company and their product, right? Everyone talks about how they can build the best boards, the best density. If you can't measure and assure that you're doing that or build that kind of a product repeatedly, how do you make those claims as a business owner and then, feel great going home at night? Like for me, if I made a claim in terms of what our lab can do, like we have to have AS9100 and our ISO 17025 certifications that like actually have the data to back up what we're, and support what we're claiming. But, it's required a lot of money on my side to just procure some of this equipment and then to figure out how to use it. And when I put on my board hat and I look at what's been going on, I think the two biggest things to me that have turned this problem from it's not that big of a problem to suddenly now it's hot and heavy. We need to figure out now is the labor market is pretty constrained. Skilled operators coming into our industry is not something that, like I said, like it's difficult for people to hold on to them. People are aging out faster than we're bringing in new talent and bringing them up to speed. It's an issue we've known about in engineering for decades. I remember going into college and all my teachers talking about they called it the gray wave coming through of people aging out and how it's going to be great for your career. Only to really realize what that means is you're going to get hired and the person retires the next day. And suddenly all these issues that have been solved, right? You don't have that tribal knowledge to figure it out. So you're seeing this compounding effect of labor, lack of internal talent and knowledge and know-how, as well as increasing complexity on the electronics portion, right? Moore's law isn't dead. Moore talked about packaging being the next frontier. So now we're having to step back down into our world to figure out where we need to optimize. And that need just hasn't been painful enough for manufacturers to make those investments, to the point now where they don't know how to make those investments because they look at how do we find a crack in a Microvia? Oh, we got to go throw it in a FIB-SEM, unit. Yeah. And it's like, okay, so now you have to identify where the crack is. You have to tell the operator what you're looking for and kind of babysit them as they figure out where that trench needs to be. And then you need to sit there and figure out, based on how do I read this report and then understand where in my process it was affected. That information, or I'd say talent pool to figure that out, it's incredibly costly. And board shops like, it's how much for a FIB-SEM gun? Like, how do we do that with our existing technology is really what I looked at. I was like, okay, how do we do it?
There's a nanofab lab at Portland State that would give this as a service to companies in the area. And even they were like ridiculously expensive, right? You expect academics to be cheap, right? So you can just imagine how much the commercial service is.
Yeah, it's bad. Like the cheapest guns that I was finding on the market that could kind of get what we wanted, like 1.5 million or something like that. And that, you know, how does a board shop turn that into revenue? It's when it's integrated into a tool that's running 90% of the time, right? And for semiconductor margins, it's a drop in the bucket compared to what they're spending. It's 300 million for a brand new ASML tool, right? But for a board shop, 1.5 million, that's a whole new electrolysis line for a lot of these companies. It can get quite costly quite quick. So that's where automation really helps. And that's kind of why we were like, okay, a third-party lab will allow us to load all of our equipment and then offer those price points to customers. One of the cool things that from a pricing model perspective, we don't have pricing announced right now, but one of the things that I'm sticking to is that it's our differentiation between a Microvia and a PTH is not there. So a lot of places will charge more for a Microvia because it's harder for a person to hit it. Because of the automation, it's actually the same amount of effort for the equipment. It's the same tool time. If anything, it's that our data assets that we generate for a Microvia, they're a lot smaller actually. So there's less technical costs, except the processing for it and alignment gets a bit more difficult, but it's a straight flat cost. So we're hoping that will really help manufacturers be able to step into higher density scales and not really face the issues that we were just talking about, which is, you know, new pieces of equipment to measure the scale and density is not something they can afford, but hopefully we can, you know, provide that to them.
Yeah, I now see how this is a capability enabler for some companies, because maybe they can etch down to, you know, 2 mil, but they don't know if it's reliable. And this helps them actually determine that.
It's cool because then you can start going even further than that. So one of the data products we're working on right now is getting surface roughness measurements from all sides of the conductor. Because now we're not constrained to just doing profilometry on the exposed side at the manufacturer, right? After you've gone through, let's say, alternative oxide. So, but being able to look at your transmission lines and get that information out, and then start to look at different points on the micrograph, and then also step through it serially. We can now start looking at what's the surface roughness impact from a full 3-dimensional model or volumetric perspective. And that tells you what your supplier's surface roughness is. So now when you're doing, you're going down to those 2 micron line and spaces, you're trying to get down to some of those crazy densities. Or sorry, 2 mil. You said 2 mil, right? Not 2 micron.
I said 2 mil, but no, not 2 micron.
But it's like there's a gap now. How do we get from there into 2 micron, right? Because that's what some of these IC substrates are doing. And eventually the signal has to get there. But that loss can compound as you go from different points to point in the transmission line. So if we can capture that information for a board shop, it only improves the value that a board shop can bring to their end customers or to their assemblers, and prove that. It's pretty crazy, the information you can get.
So how do you do the surface roughness measurement? Is it an interferometric measurement? I mean, there are ways to do it, right? You can do AFM if you really want to. You could do an interferometry measurement, which I've seen in some papers. You could do one of the ones I've seen from like Rogers data. I don't know if they do this in at scale, but you can even measure it just from like SEM images, right?
I haven't seen that Rogers paper, but I don't want to like talk about the methods we use because we do things a little different at the moment, and it is still kind of like a work in progress. It's just, that's where I'm going to leave that.
I understand. Secret sauce. We'll just end on
show
that.
Results. We'll
just end on that by saying it's better.
It's better. I like it. It's better.
That's good enough, right? So what? One thing I saw that you had posted online recently was that you were at Apex, actually going and giving some demos on all of this. And a show like Apex is really where the rubber meets the road. So whenever someone goes and gives a demo on their equipment, whether it's Apex or PCB West or whatever, I'm always wondering, what does the reception look like? What are people saying? Are you getting good questions? Is it standing room only? Tell us what it was like for you.
I appreciate it. So Apex was our kind of soft launch of the company. We're working on getting our physical lab space built out. Some things haven't happened in time. That's fine, but we're still going to go to Apex and we're still going to demo and talk about our lab and our capabilities. So I gave a technical talk at the Tech Pavilion, and because I wanted to do more of a soft launch, I gave it a really hyper technical name. It was automated metallographic and spatial correlated metrology or something like that. And the idea was to be very technical, very in the weeds, kind of show people what we're doing to a certain degree. And it started out with pretty good attendance, but by the end of the talk, I had, every chair was filled. There was 20, 30 people standing around it, which was great. And I gave that on the day one of the convention, 2 hours in, right after lunch. And from that point until quite literally the last hour of the show, I had, nonstop people coming up to our booth, which was, a great validation of our technical thesis that it's like, okay, there's metrology gap. We're trying to solve this and get people better information quicker, et cetera. And having people nonstop come up to the booth and ask us questions. But I'd also had prepared, like you'd kind of talked about, a small demo. And in this demo, we showed just the first part of our process. We call it ingestion. So when you send us your coupons, the first thing we do is we do a full GD&T measurement of everything. We're kind of calling it like the scan for like every process to keep it ambiguous. But we, like I was mentioning, we get full dimensional GD&T analysis for every surface feature that you can see on the top and bottom. We can get a pretty insane amount of information from that. So from those images and data assets alone, we can tell you what your drill perpendicularity looks like. So you're really looking at the finished copper plating of the inside of a hole. And we can look at where it was at the top and where it was at the bottom. Basically, you can infer what the drill bit was doing. So did it, wander one direction or another? Some people call it drill perpendicularity. There's another term for it, but we can tell you that kind of information right away. We can tell you what your drill registration and offsets look like. So we can look at what are the scaling factors that were involved, as well as what are the positional errors. We can look at your imaging and your etching process. So we have a class 1 laser on one of our tools. So if there's enough distance between the top of the copper and your actual solder mask, we can measure the copper height. We can measure the base of the substrate. And we can also pick out the top of your PTH, as well as where the PTH meets the substrate below it, get those diameters, and then put together what your essentially the geometry looks like for the top of the feature to tell you what your etching factor looks like. We can look at roundness of every single pad, so you can start seeing what was the etching process look like from like a true geometric shape, if you want to put it like that. We can pull out the solder mask as well, so we can look at the whole solder mask image, and then again tell you the same things: what was its registration, what was its offsets, etc. And from that, right, we can look at not just one coupon, but 2 coupons from a board, or every coupon from a board. It takes us about 30 seconds to do that per coupon to get all that information out. We can instantaneously grade it for breakout, so IPC class 2 or class 3, so we can start actually grading your material before we begin the destructive analysis, and then start looking at the statistical information per panel, per lot. You can look at lot to lot variation. You can look at factory to factory variation. So if you built the same job at multiple locations, we can compare those data assets to see what's going on. So if you're an OEM and you have multiple manufacturing facilities that are making your part, you can see what the variation looks like just from the internal, I would say, KPIs from a factory should look like. But for the factories, they're interested in this because we can look at all of their coupons over time and actually start extracting what their shop KPIs look like, so that they know what's getting in the hand of their customers, what's escaping the factory, what does their true quality impact look like. So I'm walking people through these demos, and for the most part, people are giving us nonstop, like, just like, you can do that. And like, here's the video, here's the coupons themselves. Like, we haven't altered them. It's the same thing. And then here's the data that's come out, right? And we're visualizing and transforming it for you. But that was something that I didn't think people would be really interested in, was the non-destructive initial analysis and statistical information we can get right away. But then we showed off the other half of our demo was the serialized metallography portion of this. So we're going through and we took 36 micrographs, each one of them, they were actually spaced 10 microns apart. And from those micrographs, we can align them spatially to one another, and then we can extract out all the metal features and then reconstruct what that metal object looked like in 3D space. And then we can start doing out of plane measurements, or a term that the semiconductor folks would call virtual metrology, and be able to look at what things look like out of plane or out of reference without you having to stop and actually, go and measure a different part of the coupon. So if you can imagine having to do a face grind rather than doing a cross section, we can pull out and actually show that information. So if you're looking at contact pad for a Microvia, at the base of the Microvia, we can actually look at what was going on from a 2D perspective rather than a single 1D. So it's like doing area analysis rather than just, because I think right now it's, you take a picture of the Microvia, what's the essentially length of the pad, and then how much of that pad is taken up by the contact pad of the Microvia itself. But that doesn't tell you anything about the registration capabilities of the Microvia body to the base of the pad or to the top of the Microvia. So we can look at tilt and rotation of the Microvia as well. So what was the top half of the Microvia doing? What was the body of the Microvia doing? We can look at glass weave contact with the Microvia. So how much glass and resin is in contact with it. So if you wanted to look at, if you were having issues per se for cracking or fracturing, we could help figure that out. Or if you're like over pressing and laminating something, what was the resin squeeze out from a volumetric perspective? So we had just those two little demos to show people the data you could get out of it. And the reception was a little overwhelming, to say the least. I'm incredibly thrilled to get the people who came up and talked to us, the OEMs that came up and talked to us, and were throwing out like, what about this? What about this? And it's like, okay, that's fantastic. I'd love to get there, but we're really just focused on this part of the market for the moment. And where people saw our technology could help them in different areas of PCB manufacturing overall it was cool. It's like pinch me kind of a moment. But yeah, very, very strong positive reception overall.
That's awesome, man. I can imagine very validating. And, of course, I got to say, congratulations. It's great to get such a great reception, especially on a soft launch. I think a lot of companies really dream of getting that kind of reception when they first launch. And then also, this is a new company, but it's great to see a new electronics company that's not just trying to eliminate all the engineers with AI.
Yeah.
Which I don't think will ever happen. No. But that's a little bit of my gripe with some of the innovation that's happened here. It's like, can we just route everything and end PCB design careers across the globe?
Yeah, it'll make failure analysis labs that we perform it'll be great work for me in the future.
Oh yeah,
right? This will be fantastic.
I'll come work for you.
Yeah, but you said something actually kind of on the point, and I made a point of this in my keynote, was that we're not lights out, and that's for a reason, right? As we have to validate every report. So even though we can generate the reports automatically as well, we still look at them. Automation isn't perfect. There's always edge cases. And I can't hold automation accountable. I can only hold myself accountable or my employees accountable. So how can I expect my customers to hold me accountable if I can't hold the equipment? So I made a point to kind of make that comment in my keynote. And it's something that I see a lot of people just kind of skipping over with AI in general, is that it's a great tool. It's a cognitive equalizer, if anything. But if you don't have domain knowledge or expertise in a field, it's not going to do what you think it can do. It's being oversold and overhyped, and full disclosure, right? Like I totally missed the agentic push a year and a half ago. I remember downloading Claude Code when it was first launched in November of 24, and the MCP protocol that they'd kind of announced, and then first messing with Claude Code when it was released. And thinking like, oh, that's cool, but it's still kind of like a long ways to go. You still have to know how to prompt and background info. But since that has taken over, I think people are chasing the shiny object, it feels like. And I see it too. And you talk about routing, like auto routers have been around for ages. And there's been some pretty sophisticated auto routing techniques that semiconductors used. And they're using statistical inference. And that's what they're calling it, 2014, 2017. Hint, hint, that's AI, right? That's all it is. It's a statistical model. But an LLM is very different. LLMs are not so great at spatial understanding. It's a very different animal, and you need a totally different approach and model and technique to do so.
The comment that was just made to me actually by someone on LinkedIn is that using an LLM to design PCBs is like using a dictionary to make a ham sandwich.
Okay. I like it.
Well,
I like it.
yeah. Well, I mean, like you said, though, there's no spatial awareness other than what can be defined numerically. So unless literally everything in your spatial domain is defined numerically, in
Yeah.
order for it to be, readable as text, the LLM is probably not going to do so well.
Yeah, some of them can do some really cool things, and you can structure LLMs to have tools to take in data, spatial data, and you can give them model context, but it's not the right model for the job. And there's, again, multiple approaches that have helped with this, but to just say you could slap that in anywhere and get off and running with it, it's disingenuous is what it feels like. It's like, don't lie to yourself about this. But yeah, like I said, it's gonna lead to some great work for me in the future, and I can't wait to see it and just be like, all right, guys, show me your electrical simulations here that validated this, because this is wild.
Where do you see this going? Because you've already done a lot and accomplished a lot, and there's been a lot of great reception. So I'm just wondering what's next.
Great question. My immediate what's next is open up the facility so I can start accepting orders. But if I put on my okay, where is metrology at today? Where can we go with it? I don't think we're anywhere near the fundamental limit of information we can extract from the current IPC, specimens, coupon test specimens. And my hope is that because I sit on a lot of IPC boards, is that we can actually get some active discussion and innovation going on in this field of research, because we are going to diverge from semiconductor. We have a different process, but we are going to start facing some similar electrical, mechanical, and thermal issues, but we're going to have to solve them a different way. And if we are not considering how we're going to measure and evaluate the effectiveness of the processes that we need to make these structures, we're hamstringing ourselves. And as an industry, we are not going to continue to advance. So where I see this technology in the bigger picture of metrology overall is that we need to have a bigger discussion, saying, where is our industry going to go? And do we want to continue using micrographs? I've got my opinion of this, but what's the data say? What are some new techniques? And I'm hoping that people reach out to me to tell me what they think, and to want to get involved and figure out how as a community we can do this, because it's going to be very expensive and very difficult to do so. But if we do it as more of a community, as more of what's our market going to do overall, it'll be a fun area of research. It'll drive a lot of investment. It'll drive a lot of R&D, and making PCBs fun again.
I know I said that last question was the last question, but you just gave me this idea for another question.
Perfect.
Do you think that some of the data that you're producing will ever be standardized and then ported back over to the design tools in some way, or even the simulation tools? Because I mean, the test methods are all standardized, but the reports aren't necessarily standardized, and the formatting of the data in a digital way is not necessarily standardized either. So it seems to me that there's really a lot of opportunity here to get the feedback to the designers by maybe creating your own kind of ad hoc standard, or de facto standard, I should say, or possibly even getting with IPC and trying to come up with some sort of standard for reporting metrology data.
Yeah, no, it's something that I sit on a couple of the committees, and specifically some of the steering committees for the factory of the future and where we're going with it. And it's something that I want to talk to them about, because we can look at the model-based design. I always forget whatever it's called, but it's very underutilized, because I do agree that is the problem. I took a look at, we build our internal digital assets in such a way that it's I can export it however you want because of that exact issue. And I think, from a coding perspective, agents are really good at helping you do that. But if you have a standardized way of reporting that information, it will dramatically improve the innovation and feedback and cycle loop, etc. So yeah, I do think there is a huge opportunity for IPC to take a look at this and really help close the full loop, so to speak. And I'm happy to be at the forefront of that, because I know just enough to be dangerous to make a fool of myself when talking about signal integrity. But how those formats need to be imported into something like ANSYS, right? When you're doing HFSS, or if you're looking at, okay, how do I incorporate this into Altium's format, and how do I extract that information for Altium to be able to rerun those analysis, or from SolidWorks to rerun the thermal and finite element analysis. Having a standard interoperable data exchange is something we are working on. But incorporating metrology specifically and having a bigger discussion around it is where I think, there could be some serious fun in the future to figure out how to create that ecosystem.
As it all happens, of course, we're going to have you come back on and talk about it. Geoffrey, thank you so much for being here again. And let's see if you can set the record and be the fourth, or have a fourth appearance. You'll be the most appeared on the show.
Can't wait. Looking forward to it. Zach, thank you so much for having me back on and letting me chat a little bit about my company and where I see the industry in the future going. Thank you so much for the time.
To everyone that's out there watching, we're talking with Geoffrey Leeds, founder of Scan Labs. If you're watching on YouTube, make sure to hit the like button, hit the subscribe button. You'll be able to keep up with all of our podcast episodes and tutorials as they come out. And last but not least, don't stop learning, stay on track, and we'll see you next time. Thanks, everybody.